The first type of this question that I'm going to talk about is where you are told that where we have A given that B has happened. So we are talking about the probability of an event A given that we know that an event B happened. Now, if we're dealing with independent events, A and B don't have any effect on each other. But if we're dealing with non-independent events, the fact that B has occurred already will have an effect on the probability of A. So that's what we're really dealing with. And I'm going to use an example very similar to, or the same as, what we did a few classes ago, because you'll already have a certain degree of familiarity with the numbers, which may help with this situation. So that's why I'm reusing one of the questions from earlier in the chapter. I didn't like any of the questions in the book, so I decided we'd go back to an earlier example, and hopefully it will help because your heads are already fairly clear on these numbers. So if we take x being the numbers from 1 to 12, x being a natural number, I think in the original question it said integer. I've written out my universe as a set. So this is another opportunity to remind you of set notation, because this comes up a lot in probability questions. So our universe in this case is going to be the natural numbers from 1 up to 12, and the even numbers from 1 to 12 are going to be 2, 4, 6, 8, 10, 12. The multiples of 3 are going to be 3, 6, 9, 12. No new math so far whatsoever. And a reminder, if we were drawing our Venn diagram here, we'd have our universe, we'd have our even numbers, our multiples of 3, and we start by filling in what is common to both. So if you're doing this purely as a sets question, I'd look at my two lists and see what numbers were common to both, and I'm going to fill them in my intersection. 6 and 12 are common to both. Then I would fill in the only even and only multiple of 3 parts. So 2, 4, 8, and 10 are only even, they're not multiples of 3. And I have my multiples of 3 only would be 3 and 9. And I have my numbers that are neither even nor multiples of 3, but they are numbers between 1 and 12. And I fill them in last, and I have 1, 5, 7, and 11. And I remember, if I'm writing out my elements in my sets, I always have a dot next to each. I don't for the next version of what I'm going to do, which is this is effectively a cardinal number type Venn diagram. How many elements are there in each of these sets? So my universe is going to have 12 elements in it. Numbers 1 to 12, so I have 12 different elements to deal with. In my even set, I have 2, 4, 6. I have 6 numbers in my element set. In my multiples of 3 set, I have 4. In my intersection of my two sets, I have 2. In my multiples of 3, I have 2. In my purely even numbers, I have 4. And in my neither group category, so the complement of even and multiples of 3 would be 4. Now, so far there is no new maths. We haven't done anything different than what you have already done in Junior Cert. I'm going to use this as an opportunity to remind you of set notation as I am here, and then we're going to get to the new bit once we've established what we already know. So if I wanted the probability of getting an even number, I would have the number of ways of getting an even number divided by my total number of elements. So I get probability of a half. I want the probability of getting a multiple of 3. I'd have the number of ways of getting a multiple of 3 divided by the total. This should all be fairly standard to you at this stage, but I need to be sure of it for where we're going with this. If I wanted to get the probability of M3 complement, what does complement mean? It means everything but. So what is not in my circle M3? Well, I have 4 elements out here, 4 elements out here, so I have a total of 8 out out of 12, which simplifies to 2/3. So this is effectively not M3, it's what isn't included in multiples of 3. And I again link back to a very important fact. If I have my multiples of 3 is equal to 1 minus my multiples of not 3. So linking back again, that's a formula that we keep touching on. And I'm going to write it out just to remind you of it. 1 minus not that. Okay, just to link it back in. Now, any other set notation, we need probability of even intersection multiple of 3 would be probability of even and multiple of 3. So remember, intersection and mean the same thing. So even and multiple of 3 is, we have two elements there. It's the 6 and the 12 out of a total of 12 possible outcomes. So we'd have 2 out of 12 would be probability of a sixth. And let's do union as well. And we know that union in English would be or. So this is and, this is or. So union would be everything in here. So it would be 4 plus 2 plus 2 would be 8. Out of 12 would be, sorry, what am I saying? Would be 2/3. So those are our different pieces of set notation that we already know, and I have missed one. If we have probability of even not, I'm over highlighting that for a reason, multiple of 3. That means probability of even but not multiple of 3. So we're inside the circle even, but we are not inside the circle M3. So that would leave me with 4 out of 12. Be a third. So again, probability of even, and then our slash M3 is not. So that symbol there means not. So even not M3 is we're inside the circle even, but we are not including anything from multiple of 3. So that'd be 4 out of 12. So that's a symbol you also already know. One that we haven't come across before, and what we're going to do now, I'm going to write it in English first. What's the probability of even given that we already have a multiple of 3? Now let's look at what this would be like in an English sentence. If we're told that we have picked one of our numbers, so if we're just told that we pick a number, we know that we're picking from a group of 1 to 12. But if we're told when we're playing a game or something that we pick a number and we're told that the number is a multiple of 3, so we are given that it is a multiple of 3. Given that it is a multiple of 3, what is the probability that it is even? So now we aren't picking from a group of 12 numbers anymore. We know that we're picking from a group of 4 numbers because we know it's a multiple of 3. So there's only 4 possibilities. So we know that we are dealing with a multiple of 3. What's the probability that it is even? Well, if we know we're inside the circle multiple of 3, what's the probability that it's even? Well, the only even numbers that are also multiples of 3 are the ones in here. So that's going to be 2 out of a total of 4, which simplifies to a half. Let's do the opposite of that. Given even. Again, in an English sentence, we've picked a number out from our list, 1 to 12. If we're told that the number that got picked is even, what is the probability that it's also a multiple of 3? So what's the probability of having a multiple of 3 given that our number is even? We're given that it's even, so we are definitely in this group. We're inside this circle. So we have 6 possible outcomes in total. How many of them are multiples of 3? Well, there's only 2 outcomes here that are in our circle even and also multiples of 3. So it's going to be 2 out of our total of 6 possibilities. Because we know that it's even, we only have 6 possible outcomes. That's going to be a third. Now if we look at what we've done here, probability of even given multiple of 3. If I write that out again, what did I actually do if I look at my Venn diagram? I had the total that I'm working from is I must be a multiple of 3. So I have the number of ways that I can be a multiple of 3. And where did my 2 come from? It was the multiples of 3 that are also even. Well, what's the way of writing that in set notation? It would be cardinal number of E even intersection multiples of 3. So this is taking from my Venn diagram what I argued out in English. The probability of E given of even given that it is a multiple of 3 is the number of ways that I have even numbers that are also multiples of 3. So even intersection multiples of 3 divided by my new total, which is my number of ways that I can be a multiple of 3. So this is a very important formula, and I'm going to write it in its set language now. So E vertical line multiple of 3 would be cardinal number of E intersection multiple of 3 all over cardinal number of multiple of 3. And hopefully you are happy with where that argument is coming from. Now, this is not the form we often use this in. We often recognize that we can divide above and below by 12 and turn these two into probabilities. So the other way of writing this, probability of A given B is equal to the probability of A intersection B all over the probability of B. And hopefully you're happy with where that comes from. Rearranging this formula, multiplying both sides by B, would give us an equation for probability of A and B, which we often want. So if we rearrange that, multiply both sides by B, we get probability of A intersection B would be equal to probability of B multiplied by probability of A given B. Now, we often write this in a different order because we generally like to deal with probabilities of A's. Just because of our prejudice, we know that probability of A intersection B must be equal to probability of B intersection A. So you could rewrite that formula, making A the subject, as probability of A intersection B would be equal to probability of A multiplied by probability of B given A. Now, this formula and this formula and this formula must be memorized. I've tried to give you an argument for where they are coming from, but you have to know them by heart